Welcome, everyone. Mamoru is going to tell us about affine Yangians and W-algebras. Feel free to start whenever you're ready, Mamoru.
Okay, thank you very much for introducing me. And I also appreciate the organizers for giving me a chance to talk. Today, I'd like to talk about how to construct a homomorphism from the affine Yangian, which is one kind of quantum group, to the universal enveloping algebra of W-algebra, including non-rectangular cases. And actually, 2 years ago, at this seminar, I talked about how to construct a homomorphism from the affine Yangian to rectangular W-algebras. And this talk is a generalization of the previous talk. And I am not the, so at first I talked about the background of this homomorphism. I am not a specialist of the VOA, so maybe all of you know better than me about the W-algebra, but I'll explain about W-algebra briefly. W-algebra is a vertex algebra associated with finite dimensional reductive algebra and its nilpotent element, and one complex number, which is called level. And the easiest example of the W-algebra is that case f is equal to 0. Then in this case, the W-algebra is equal to the universal one-prime vertex algebra. And the defining relations of the universal affine vertex algebra is equal to the defining relations of affine algebras. However, for a more general case, it is so complicated that we cannot easily write down the defining relations of a W-algebra directly. However, the finite analog of the finite analog of a W-algebra, which is called the finite W-algebra. In this case, Brandon Khrushchev wrote down defining relations of the finite W-algebra of type A. That is, the Brandon Khrushchev wrote down a finite W-algebra of type A as a quotient algebra of the shifted Yangian, which is a subalgebra of the finite Yangian of type A. So my main goal is to construct the affine analog of the work of Brandon Khrushchev. So next, I'll talk about how to. I'll talk about the finite W-algebra and finite Yangian briefly. The finite W-algebra is an associative algebra associated with a finite dimensional reductive algebra and its nilpotent element. And the finite W-algebra is a Z-algebra of a W-algebra. So it is a quotient of a W-algebra as a vector space. And one of the easiest example of the finite W-algebras is that in the case a nilpotent element is equal to 0, then the finite W-algebra becomes the universal enveloping algebra of the original and the algebra. And in the case that the nilpotent element is equal to 0, the W-algebra becomes the universal affine vertex algebra whose defining relations is equal to those of the affine algebra. So we can say that the finite W-algebra is a finite analog of a W-algebra. This is the easiest example. The finite Yangian, on the other hand, the finite Yangian is one kind of quantum group. That is, the finite Yangian is a Hopper algebra associated with a finite dimensional simple real algebra and one complex number. And if this complex number is equal to 0, then the finite Yangian coincides with the universal enveloping algebra of the current algebra. And so we can say that the finite Yangian is a deformation of the current algebra. One of the features of the finite Yangian is that the finite Yangian associated with SLN has a homomorphism from the finite Yangian to the universal enveloping algebra of SLN. This algebra is called, this homomorphism is called the evaluation map because if we take the complex number h is equal to 0, then the finite Yangian is equal to the universal enveloping algebra of the current algebra. So it contains the SLN coefficient polynomial. Then the evaluation map maps this evaluated SLN coefficient polynomial FU to F0. So this is a substitution of 0 to U. So we say this evaluation map, this map is evaluation map. And also, W-algebra associated with a nilpotent element 0 is equal to the universal enveloping algebra or the original Lie algebra. So the universal enveloping algebra of SLN is one of the easiest example of the finite W algebra. So we can consider this evaluation map as the easiest example, simplest example of the relationships between finite Yangians and finite W algebras. And Lagosian solver gave the generality of the evaluation map that they gave a surjective homomorphism from the finite Yangian associated with SLN to the finite W algebras associated with SLN and its nilpotent element of L to the power of N. And we say the W algebra associated with GLN or SLN and its nilpotent element of type L to the power of N, a rectangular W algebra or rectangular finite W algebra, and we denote like this. And in the case that N is equal to 1 case, the algebra becomes GLN, and the nilpotent element becomes the principal nilpotent element of the GLN, L. So we call this algebra the principal W algebra. And also, in the case that L is equal to 1 case, then in this case, this algebra is GLN, but its nilpotent element is equal to 0. So in this case, the finite W algebra associated with such Lie algebra and its nilpotent element F is equal to the universal enveloping algebra of SLN. So Lagosian solver's homomorphism is equal to the evaluation. And Brandon Khrushchev gave the generalization of the result of the Lagosian solver. They used the shifted Yangian. So next, I'll talk about how to define the shifted Yangian. Let us take the Chevalier generators of the real finite dimensional real algebra again. And we denote them hi and xi plus minus. And the finite Yangian is a deformation of the universal enveloping algebra of the current algebra. So at first, we consider the natural generators of the current algebra, currently algebra. And now by taking these Chevalier generators, current algebra has natural generators, hi tensor u to the power of r, or xi plus minus tensor u to the power of r. And so, since the finite Yangian is a deformation of the current algebra, so they have the presentation whose generators are corresponding to these elements. And we could denote these elements HR and XI plus minus. And we call this presentation the current presentation of the finite Yangian. And by using this presentation, the shifted Yangian can be defined as follows. We take an anti-dominant dominant co-weight of J. Then the shifted Yangian is a subalgebra of the finite Yangian associated with such pattern and generated by these elements. So, and xi plus, as for xi plus, the index is same as the finite Yangian. However, as for hi and xi minus, the relation is a little shifted by minus beta alpha. So we call this algebra the shifted Yangian. And in the case that beta is equal to 0 case, then the shift is equal to 0. So the shifted Yangian coincides with the finite Yangian. And Brandon-Khrushchev wrote down by this in the type A setting. Brandon-Khrushchev wrote down the finite W-algebra of type A by using the quotient algebra of such shifted Yangians. So we would like to make the affine analog of the Brandon-Khrushchev work. So the problem is that what is the relationship between the affine Yangian and the W-algebra? In the rectangular case, at first, in the case L is equal to 1 case, Gui gave a homomorphism, which is called the evaluation. Evaluation map is a surjective homomorphism from the affine Yangian to the completion of the universal enveloping algebra of KL hat. And in the case that F is the nilpotent element is equal to 0, then W-algebra coincides with the universal affine vertex algebra. So this becomes the universal enveloping algebra of the universal affine vertex algebra. So Gui gave the easiest relationship between the affine Yangian and the rectangular W-algebra. And in the principal nilpotent element case, Shihman Barcelo gave a surjective homomorphism from the affine Yangian associated with scale hat 1. This affine Yangian can be defined geometrically to the universal enveloping algebra of the principal W-algebra. And moreover, Shihman Barcelo gave a geometric representation of the principal W-algebra by using this homomorphism. In physics, this is corresponding to the resolution of the AGT conjecture. And more general rectangular case, I gave a surjective homomorphism from the affine Yangian to the universal enveloping algebra of rectangular W-algebra. And in the non-critical case, this homomorphism becomes a surjective. And so we would like to consider more general case, that is non-rectangular cases. As for non-rectangular cases, Krotik-Diakonet-Ma conjectured that there exists a surjective homomorphism from the shifted affine Yangian to the universal enveloping algebra or iterated W-algebra. It is conjectured that iterated W-algebra is isomorphic to the W-algebra and the tensor of the Heisenberg beta gamma systems. So we can say that this is affine analog of the Brandon-Khrushchev work homomorphism. And also, Krotik-Diakonet-Ma conjectured, but that through this homomorphism, we can construct a geometric representation of iterated W-algebra on the equivalent cohomology of affine Riemann spaces. However, the shifted affine Yangian is very, very complicated. So it is difficult to construct such surjective homomorphisms, not directly. So we would like to consider the one strategy. The shifted actually, let us go back to the work of Brandon-Khrushchev. Actually, the shifted Yangian has a finite Yangian as a subalgebra. So the restriction of the Brandon-Khrushchev homomorphism to this finite Yangian, then we can obtain a homomorphism from the finite Yangian to the general finite W-algebras of type A. And actually, by Desor-Katzpah-Levy, this algebra, this homomorphism was obtained by using the Lax operator. So I try to construct the affine analog of this homomorphism. And also, I would like to extend this homomorphism to the shifted affine Yangian. Then I hope that we can obtain the affine analog. I hope that we can resolve the quadratic Diagonetz conjecture. So this is the main theorem, which is a affine analog of Diagonetz quadratic Diagonetz conjecture that we can construct homomorphism from the affine Yangian to the universal enveloping algebra of the rectangular as a non-rectangular W-algebra. And also this homomorphism becomes the affine analog of the Descartes barrés, context barrés homomorphism. Yeah. So next, I talk about the detail.
Wait, Mamoru, can you go back? Why does the nilpotent have such a specific shape?
Actually, this is general shape because we can.
I see.
Sorry. Yeah, we can take any nilpotent elements of KL can be written as follows.
Okay, so F can be any nilpotent element in this result. Is that right?
Okay. Yeah.
Okay, thanks.
And so next I talk about Yangian more in detail. The finite Yangian is one kind of quantum group that is and it is a deformation of the current algebra. And the current algebra is a real algebra whose vector space is J tensor 1 polynomial ring. And the commutator relations of this algebra comes from naturally from K and 1 polynomial ring. So when considering the definition of the finite Yangian, at first we should consider the definition we should consider the presentation of the universal enveloping algebra of the current algebra. And when we take the HI and XI plus minus as Chevrolet generators of K, and then there exists a natural generators of the current algebra such that HI tensor U to the power of R or XI plus minus tensor U to the power of R. And this is a presentation whose generators are corresponding to XI tensor plus minus tensor U to the power of S and HI tensor U to the power of S. And differentiations are given as follows. The first three and last three relations come from J, and these two relations come from the one polynomial ring. And the finite Yangian is a deformation of the universal enveloping algebra of the current algebra. So in order to define the finite Yangian, we should deform these relations. And actually, this is the definition of the finite Yangian. These four relations are same as those of the current algebra, and we add these two terms and to the defining relations. But if we set h is equal to 0, then these two terms vanish, and the defining relations coincide with the current algebra. So we can define, the finite Yangian becomes the formation of the current algebra. And looking at this definition, we find that we can define the Yangian for symmetrizable Kac-Moody algebra by the same way. And actually, in the case that J is a affine D algebra, the Yangian defined by this formula has a coproduct, and also they have a Hopper algebra structure. So we can say that the affine Yangian is a quantum group, one kind of quantum groups. So we can define the affine Yangian associated with SL pattern by this defining relation. However, in order to construct a relation between affine Yangian and W algebra, we need to consider the two-parameter affine Yangian which was first introduced by Gray. This is a definition given by the Gray. Actually, the difference between the one parameter Yangian and two parameter Yangian is here. We add these two terms. But if we set epsilon1 and epsilon2 are equal to half of h, then this definition coincides with the one parameter case. So this definition of the affine Yangian given by the Gray was the very natural extension of the first one. And so it also has a coproduct and Hopper algebra structure. So it becomes a quantum group. And this coproduct was given by Gray and Gray-Nakajima-Wendlandt. And also Gray shows that in the case that epsilon1 and epsilon2 are equal to 0 case, then this affine Yangian coincides with the universal enveloping algebra of universal extension of SLN U plus minus 1 V. So it has a quantum group structure. And one of the difficulties of the definition of the affine Yangian is that the number of the generators is infinite. However, Gray and Gray-Nakajima-Wendlandt introduced and the minimized presentation whose number of generators are infinite. And actually, in this presentation, generators are HI0 or HI1, XI0 plus minus, and XI1 plus minus. And other generators can be given inductively as follows. If you consider the H equals 0 case, this construction is very simple. If you would like to construct a homomorphism or representation, you only need to consider where these generators are mapped, and it will be compatible with this minimalist presentation or not. So this is very, very strong result. And by using this minimalist presentation, Gray constructed a homomorphism from the affine Yangian to the universal enveloping algebra of Gale-Hartman. And this algebra is called, this homomorphism is called evaluation. And also, Cordera shows that this homomorphism is surjective. So this is the easiest example of the relationship between affine Yangians and affine between W-algebras, because Gale-Hartman is isomorphic to the universal enveloping algebra of W-algebra with associated with a nilpotent element 0. And also, the affine Yangian has an operator which is called a shift operator. The shift operator is determined as follows. The meaning of the shift operator can be given in the symmetrizable Katsumi-DD algebra, and actually this shift operator can be defined for any symmetrizable Katsumi-DD algebra. So let us consider the case that J is a finite dimensional simple real algebra, and the parameter is equal to 0. Then the finite Yangian coincides with the universal enveloping algebra of current algebra, and shift operator acts to the finite current algebra as follows. For any element, x tensor u to the power of r in the current algebra is mapped to x tensor u plus a to the power of r. So if r is equal to 0, then x tensor 1 is corresponding to x tensor 1. So hi0 is corresponding to hi0. And if r is equal to 1, x tensor u is corresponding to x tensor u plus a. So hi1 is corresponding to hi1 plus a hi0. So this is the meaning of the shift. And also, in order to construct a homomorphism, construct a coproduct for the affine Yangian, we need to take the degrees completion of the affine Yangian. We set a degree of the affine Yangian as follows. We take the degree of hi0 as 0, and we also set a degree of xi bar plus minus is, if I is equal to 0, then it is plus minus 1, and if otherwise, it is equal to 0. And actually, there exists a natural homomorphism from the universal enveloping algebra of affine D algebra to the affine Yangian. It is determined by hi is mapped to hi0 and xi plus minus mapped to xi0 plus minus. And there exists a natural degree on the universal affine D algebra that is the degree of eij tensor t to the power of r is equal to r. And this degree is compatible with the natural degree of the affine D algebra. Then we can take standard degree as completion of the affine Yangian by using this degree. Then we can define algebral homomorphism from the affine Yangian to the degree-wise completion of the tensor of the affine D algebra. And Ueda Nakashima's rendezvous shows that this algebra, this homomorphism satisfies the coassocitivity. So we can regard this homomorphism as a coproduct for the affine Yangian. Okay, so next, I'll talk about how to construct a homomorphism from the affine Yangian to rectangular W-algebras, and I'll give you the new meaning of this homomorphism in this talk. W-algebra is a vertex algebra defined by the quantum Dirichlet-Stokes reaction, and it is associated with a finite dimensional reductive algebra and its nilpotent element and one complex number, which is called level. And in this section, we only consider the rectangular case, that is, J is GLNL, and F is a nilpotent element of L to the power of N. And in order to construct the homomorphism from the affine Yangian to W-algebra, one of the problem is that the W-algebra is a vertex algebra, so not associative algebra. So we need to consider the associative algebra, which gives the information of W-algebra. So we consider the universal enveloping algebra or vertex algebra. Maybe, as you know, the universal enveloping algebra or vertex algebra is associative algebra, whose defining relations of is equal to the relations of V. So if we consider a W-algebra, if we consider the universal enveloping algebra of a W-algebra, we can obtain the information of the W-algebra perfectly. So I will give one example of the universal enveloping algebra. The universal enveloping algebra of the universal affine vertex algebra becomes the degree-wise completion of the universal enveloping algebra of KL hat N. So the evaluation map, which is given by Gray, is a simplest example of the homomorphism from the affine Yangian to the universal enveloping algebra of W-algebra, because it is a homomorphism from the affine Yangian to the degree-wise completion of universal enveloping algebra of KL. And so, in order to consider the homomorphism from the affine Yangian to rectangular W-algebra, actually, we would like to use evaluation map for the proof, for the construction of the homomorphism. So we would like to relate the W-algebra to something universal enveloping algebra of K head hat. So we would like to take the mirror map. We could consider the case that J is equal to JNN, and we take any nilpotent elements, and so Q1 and Q2 and QL satisfies like this condition. And then there exists injective homomorphism called the mirror map, which gives embedding from the W-algebra to the tensor product of the universal affine vertex algebra. We consider the universal enveloping algebra of both sides. We can obtain injective homomorphism from the universal enveloping algebra of a W-algebra and universal enveloping algebra, the tensor product of the universal enveloping algebra of GL hat. Okay, so now we finished the preparation for the proof of the how to construct of the construction of the homomorphism from the affine Yangian to the rectangular W-algebras. And this is the main result in this section. We assume that n is greater than or equal to 3 because in order to construct the minimalistic presentation of the affine Yangian, we need this condition. And also, we assume that L is greater than and equal to 2. In the case that L is equal to 1 case, W-algebra is equal to the universal affine vertex algebra. So Gue already gave a homomorphism from the affine Yangian to the rectangular W-algebra. It is nothing but evaluation map. And we also take 2 parameters which are dependent on K and L. Then we can obtain a homomorphism from the affine Yangian to the universal enveloping algebra of rectangular W-algebra. And also, the level is on the non-critical level. Then the image of this homomorphism is dense in the target. So any representation of rectangular W-algebra can be regarded as a representation of the affine Yangian, and also the non-critical level, the irreducibility of the representation can be preserved via this homomorphism. And at first, I constructed this homomorphism by a direct computation. However, Cordera and I gave another proof of this homomorphism. Actually, Cordera and I construct this homomorphism by using the coproduct and evaluation map and shift operator for the affine Yangian and mirror map. The proof is as follows. At first, we consider the composition of the coproduct. Then we obtain a homomorphism from the affine Yangian to the Earth tensor of the affine Yangian. And this is the definition of the coproduct for the affine Yangian. And also, we obtain composing the Earth tensor of evaluation map and Earth tensor of the shift operator. We obtain a homomorphism from the Earth tensor of the affine Yangian to the Earth tensor of universal enveloping algebra of GL hat. So then we obtain, by these 2 homomorphisms, we obtain a homomorphism from the affine Yangian to the Earth tensor of the universal enveloping algebra. And also, the universal enveloping algebra of rectangular W-algebra can be embedded into the Earth tensor of the universal enveloping algebra of GL hat via the mirror map. So, if we can construct phi n satisfying this homomorphism, then we find that because these 3 maps are homomorphism, and this the mirror map is injective, so phi n becomes injective. So this is how to construct phi n for the affine Yangian and rectangular W-algebra. And this proof gives the relationship between the coproduct for the affine Yangian and the coproduct for the rectangular W-algebra. So this is the meaning of, this proof is the meaning of phi n from the perspective of n. So it is natural to consider the question, what is the meaning of this phi n from the point of n? And in the recent work, I gave the meaning of phi n from the perspective of n. I have constructed a homomorphism from the affine Yangian associated with SL hat n to the affine Yangian associated with SL hat n plus n. And also, there exists a natural embedding from rectangular W-algebra associated with scale 2n and the nilpotent element of type 2 to the power of n can be embedded into the larger rectangular W-algebra associated with scale 2n plus 2n and its nilpotent element of type 2 to the power of n plus n. And I conjecture that maybe there exists a natural embedding for any L, but this embedding was proved by using the direct computation of the OPs. So, and I don't know how to compute the direct the OPs of the general case, the rectangular W-algebras in general case. So I don't know whether there exists a natural embedding. So anyway, in the case that L is equal to 2 case, I know that there exists a natural embedding. So, and also we have this commutative diagram. It means that phi n coincides with the composition of psi1, this homomorphism, and phi n plus n. So we can consider phi n is one kind of the restriction of phi n plus n in this map. And also, if we can show that there exists a natural embedding from the general L or general L, then by the definition of psi1, we can show this commutative diagram in the natural L. So maybe this is so this is the meaning of phi n from the perspective of n. And more generally, we can extend this homomorphism psi1 to the whole as follows. By using another construction, we can construct a homomorphism from the affine Yangian associated with SL hat n to the affine Yangian associated with SL hat n plus n. We assume that m is greater than or equal to 3. Then, and also, the images of psi1 and the images of psi2 are commutative with each other. So we can construct, so psi1 tensor psi2 gave a homomorphism from the affine Yangian associated with SL hat n tensor for the affine Yangian associated with SL hat n to the affine Yangian associated with SL hat n plus n. And by using this my main theorem, my theorem, by composing by this homomorphism, we obtain a homomorphism from the affine Yangian associated with SL hat n to the coset of two rectangular W-algebras. And actually, this is in the case k plus n plus n is not equal to 0 case, the image of psi1 is here. Because psi is, the image of phi m and psi1, the composition of the psi1 and phi m plus n is here. And we show that we have already shown that these two are commutative with each other. So it's the image of psi2 contains in the coset of the this homomorphism. So we can obtain this homomorphism. So this is one of the meaning of the my homomorphism from the perspective of N. Yeah. So next, I talk about how to construct the homomorphism from the affine Yangian to rectangular W-algebras. So at first, let us go back to the Brandt-Kreshchev work. The Brandt-Kreshchev wrote down the finite W algebra of type A as a quotient algebra of the 60 Yangian, which is a subalgebra of the finite Yangian associated with an anti-dominant co-weight. And in this case, we only consider the case that the real algebra is equal to SLN case. Then this is the definition. And if we said beta is equal, the anti-dominant co-weight is equal to 0, then there are no shifts. So the 60 Yangian coincides with the finite Yangian. And also, the 60 Yangian, if we take the dual basis of the simple weight of alpha y, we denote them alpha I star, and then we can write the co-weight as follows, and SP plus 1, and so on, SR is equal to 0 case. Then this 60 Yangian contains the finite Yangian associated with SLR minus P plus 2. So if we restrict the Brandt-Kreshchev homomorphism to this finite Yangian, we obtain the homomorphism from the finite Yangian to non-rectangular W algebra, to general finite W algebras of type A, and that is the homomorphism given by Desel-Kaczmarelli. And also, there exists a homomorphism such that it is corresponding to the coproduct, but this homomorphism is, there exists a homomorphism from the 60 Yangian to the 60 Yangian to the UDLN. We note that the shift here and here are different with each other. It is a little approaching to 0. So if we compose such a delta again and again, we obtain that the 60 Yangian to the finite Yangian tensor UJ. And this homomorphism is corresponding to, in the finite setting, finite Yangian's case, this homomorphism is corresponding to the coproduct and the composition of coproduct and identity map tensor evaluation map. So we can show that we can construct the Brandt-Kreshchev homomorphism by using this homomorphism. And also, in the Brandt-Kreshchev work, the 60 Yangian is 60 Yangian associated with JLN, not SLN. However, 60 Yangian associated with SJLN also has the same feature of the 60 Yangian associated with SLN. So we can use these homomorphisms or these features. Now, next, I talk about how to construct Brandt-Kreshchev homomorphism. We take any nilpotent of KLN as follows. N can be divided into L1 Q1 plus L2 Q plus 2 plus L2 Q plus 2, and Q1 is greater than Q2. Then the finite Yangian is the finite W algebra associated with such DLM and such nilpotent element can be written down as a quotient algebra of the 60 Yangian associated with this Q1, and the co-weight can be given as follows. The proof was very similar to the one for Codera and my another proof about the homomorphism from the affine Yangian to the rectangular W algebras. At first, we compose the homomorphism of this homomorphism. We compose this again and again of this homomorphism. Then we obtain a homomorphism from the 60 Yangian to the finite Yangian tensor universal enveloping algebra of KL. And also, Lagosian solver constructed the homomorphism from the finite Yangian of type A to the rectangular finite W-algebras. However, rectangular finite W-algebra can be constructed, can be embedded into the universal enveloping algebra of KL by using the mirror map. So the Lagosian solver's homomorphism gave a homomorphism from the finite Yangian tensor universal enveloping algebra of KL to the tensor of universal enveloping algebra. And also, mirror map gave an injective homomorphism from a finite W algebra to the universal enveloping algebra. And if we can construct phi satisfying this homomorphism, this commutative diagram, then these three are homomorphism and mirror map is injective. So we find that this map is also homomorphism. This is how to construct the Brandon-Questius homomorphism. So by the similar way, so we expect that by a similar way, we can construct a homomorphism from the shifted affine Yangian to the general W algebra. However, the shifted Yangian is very, very complicated, so it is difficult to construct this homomorphism. And so we consider—
Wait, Mamoru, but
yeah.
have you resolved the conjecture for type A? Is that what you're saying? And then you hope to do it for other types?
No, just type A case.
You have resolved it for type A, though. Just making sure I understand that. Is that correct?
Yeah, that's correct.
Gotcha. Thanks.
So yes. So we would like to construct the affine analog of the Dirac-Delsorme-Kaczmarek homomorphism. That is a homomorphism from the finite Yangian of type A to the finite W algebra of type A. And so this is the main theorem of this talk. And I have constructed a homomorphism from the affine Yangian to the universal enveloping algebra of type A, the general W algebra of type A. We take QL is greater than or equal to 3 because in order to define the affine Yangian, we need to take this condition that we use in order to use the minimized presentation of the affine Yangian, we need to take this condition. And also, we set epsilon1 and epsilon2 as follows. They are dependent on the K and QL. And then we can construct algebra homomorphism from the affine Yangian to the universal enveloping algebra of a general W algebra of type A. We can prove this theorem in the same way as the Codera and Amit. But in order to construct a homomorphism, we need to extend the affine Yangian associated with SLN hot N to the new associative algebra associated with A. A is an integer greater than or equal to N and satisfies the following three properties. The first property, there exists two homomorphisms. The first one is a homomorphism from the affine Yangian to the new associative algebra. And the second homomorphism is a universal enveloping algebra of the homomorphism. And there is another one is a homomorphism from the universal enveloping algebra of the hot A to the new associative algebra. And the new associative algebra is generated by these two images. And also, the new associative algebra has a map corresponding to the evaluation map. That is, this evaluation map is a homomorphism from the new associative algebra to the standard degree-wise completion of UDL hot A. And also, this new associative algebra has a coproduct corresponding to the coproduct for the affine Yangian, that if A is greater than or equal to B and B is greater than or equal to N, then there exists a homomorphism from the new associative algebra associated with B to the new associative algebra associated with A tensor, the new associative algebra associated with B. This is corresponding to the coproduct for the affine Yangian. Then, by using these three properties, we can construct a homomorphism from the affine Yangian to the general W-algebra. First, by composing of this coproduct, we obtain homomorphism from the affine Yangian to the tensor product of the affine Yangian. And next, we can compare the tensor product of the evaluation map. We obtain a homomorphism from the affine Yangian to the universal enveloping algebra with L hat. And by using the mirror map, the universal enveloping algebra with W-algebra can be embedded into the universal enveloping tensor product of the universal enveloping algebra of L hat. So if we can construct phi satisfying this commutative diagram, then we find that this becomes a homomorphism. This is how to construct a homomorphism from the affine Yangian to the general W-algebra. And the Dedekind, and also this becomes the affine analog of the Dedekind-Katz-Barrés homomorphism. So I expect that by extending this homomorphism to the shifted affine Yangian, then we can resolve the Dedekind-Katz-Barrés conjecture. And I have already constructed a homomorphism from the affine Yangian associated with SL hat n to the affine Yangian associated with SL hat n plus n. So in a similar way, I hope that we can construct a homomorphism from the affine Yangian to the shifted affine Yangian. And by using this extension, we can resolve that Grote-Diaconet-Math conjecture. Thank you for listening.
Thank you so much, Mamoru. I'm going to stop the recording so that we can move on to questions. Thank you. Give me 1 second.